over on the edge of the continent, what used to be the edge of the rift system, before it spread so far that we've got an ocean and a mid-ocean ridge and everything like that, it does continue to change for quite a while. It's called a passive margin because there's no subduction, no serious earthquakes. All the tectonic activity is very old by the time it's a coastline. But if we use seismic equipment and look at what's going on under there, we can see the old remnants of the rift. We can see these listrict faults, these half-grabens. We can see where it was covered in salt from the early stage when the sea was coming in and out and drying up and evaporating. We can see this coastal plain and collapse downward and outward. So this is all sediment washing out to the shore and then collapsing down and spreading very slowly, millions of years, out over the salt, mixing with the salt due to buoyancy concerns. Sediment is usually more dense than the salt, so you get upwells of salt, little salt domes and stuff, which we talked about before, until we get to the edge of the continental margin. We have the continental rise, and then we're out in the ocean over the oceanic crust. So all of these faults, all of these salt structures are present at a passive margin because of the extension system that was present. These are relics that are now inactive. We also have thermal subsidence because the crust has cooled so much, it is so far away from that rift that it has been sinking. Okay, sorry if this is a little disjointed. I had to pause my recording, and so I'm just back now. And we were about to talk about causes of rifting. One of the possible causes is when there's a mantle plume and the upwelling and the heat involved in that mantle plume can weaken the crust and cause stretching over the plume. Now, one thing to keep in mind here is that this plume, the way it's drawn here, looks very fluid. You know, a lot of times mantle convection is compared to like a lava lamp, and we see the globs going up and down in the lava lamp, and they're very, very fluid. However, these mantle plumes are solid rock. They're solid, but they can behave plastically due to the extreme heat and pressures involved. And so this plume, to move like that, takes 100 million years to rise and bulge out like that. This is not a quick fluid action like it can easily be interpreted from the drawings like this. We can also get rifting when we have subduction. This might seem a little counterintuitive at first. Hey, subduction is a collision zone, there's compression, but within that lithosphere that is being subducted, it's being bent. And when you take something really thick and solid and you bend it, you have stretching on the upper surface. That stretching is rifting and thinning as it gets stretched. And so you can see here, a kind of simplified, cartoonified version of the rifting that can happen on that upper stretched curved surface of that downgoing slab We can also see it simply from gravity collapse of very tall mountain ranges. It's like the Himalayan mountains aren't going to get taller because the rate of rise is being balanced out both by the rate of erosion and the rate of collapse. The mountains have a limit based on the strength of the rock and the temperatures involved deep down inside the mountains, to where if they're too tall, they just collapse. The rock fails due to that extreme pressure, the weight of the rock that's been uplifted. And so we get basically extensional collapse of a mountain, which acts like rifting in a sense, in the fact that the fault types are the same, there is extension, and it is thinning. It's, going from 8 kilometers tall to 7.5 kilometers tall, or something like that. We can also have another type of extension relating to a subduction zone called back arc extension. Now, the way this works is that this overriding plate is moving left, or maybe west, depending how this cross-section is oriented, but it's not moving west as fast as this subducting plate. That's why it can actually subduct. So, say this top one's moving west at 3 centimeters a year, and the subducting plate is moving west at 6 centimeters a year, it's going to hit and it's going to subduct because it's going 3 centimeters a year faster. However, it can experience something called rollback. What this is like is if you take a piece of thick paper and you have it sitting on a table and you slowly push it so that it starts sticking out over the edge of the table. At first it stays straight and then it starts bending. As more and more paper gets pushed out, the weight of that paper pulls it down, and that bend point actually moves closer to the table as you push more paper out. As more slab is subducted and there's more weight pulling down, it pulls that bend back, in this case eastward. If that rollback exceeds the speed difference between these, so say it's rolling back at 4 centimeters a year, that means this area in the middle is now being stretched backwards because this is all adhered to that downgoing slab. We can also have failure of an old weak origin. So we had a big mountain range, it collapsed, it fractured a lot, and now it's weaker than the surrounding areas. And so because it's the weak zone, this is that structural control that decides where something rifts. If there's extension on either side of the continent, this old weak origin zone might be where the rift forms. We can also have it in transform faults, because along the length of the transform fault is not one grand straight line. We're dealing with a curved surface, different plates, lots of things going on, and there are zones where we get the pull-apart basins. I believe we already talked about this. If not, we'll go into it in more in depth later. But we can have these pull-apart basins and we can have compressional zones depending on which way the bend goes in this transform fault.